Okay, we haven't finished part 2 yet, so we found that e of x1 was equal to 3p plus 3. Now for part 2, it's asking us for an unbiased estimator for p. Okay, so we want e of something to do with x1, some function of x1, to be an unbiased estimator for p, so the expected value of the variable we're dealing with here has got to equal p. So how can we transform this guy here into p? Well, you might just be able to see that, what if I actually did the following? The expected value of, what if I did x1 minus 3 and then divided by 3? Can you see what would happen there? So this is e of x1 over 3 minus e of 1, and this would be equal to e of x1 minus 3, e of x1 divided by 3, sorry. This is just the same as 1/3 of e of x1, and e of 1 is just 1. So now if I feed in e of x1, which is 3p plus 3, so 1/3 of 3p plus 3 minus 1 equals p plus 1 minus 1, which equals p. So x1 minus 3 over 3 is indeed an unbiased estimator for p. Let's go on to the tasty one now. Okay, the dice roll the second time and the score x2 is noted. We've got to show that all of this expression, which looks crazy, is also an unbiased estimator for p. Okay? Notice this is in factored form k times by x1 minus 3, and then in factored form here as well. Okay, so let's just write down a few assumptions at the moment. We want to show that, let's put my pen back on. There we go. We need to show the expected value of all of that above expression here just comes out to be p. So there's a lot of expectation algebra. But on the side, let's just think about this. We know that e of x1 equals e of x2. And both of these guys are equal to 3p plus 3. So we have that on the side. We might need to use this at some stage. So let's just play with it. I'm going to do e of all of this expression here. But because I've got it already factorised with a constant here, it's kind of like e of a x1 minus 3 plus, b of x2 minus 3. So I'm going to immediately factor out these particular k and a third minus k. So e of all of this expression will be k times by e of x1 minus 3 plus 1/3 minus k, in bracket there, I suppose, yeah, e of x2 minus 3. Now you can have a little think about it. From this side here, e of x2 minus 3 equals e of x2, literally, minus 3. So that's equaling to e of x2, which is 3p plus 3, minus 3. So that equals to 3p. So we can actually go and substitute this 3p in here, and also in here, there's x1 and x2 is the same variable. So this is actually k times by 3p plus 1/3 minus k times by 3p. So this is 3pk plus 1/3 times 3p is p, and minus 3pk. That's equal to p. So we've done what we need to do. The expected value of this kind of messy expression here comes out to be actually p. So not too bad. Now this is talking about the efficiency of the estimator. Okay, so that's the important thing. So the efficiency of the estimator is to do with the variability. We want the variability of the estimator to be as low as possible. Alright, so we have to go and crunch out the variance of that previous expression. So we need all of this written down. So we'll bring it across and just write it down so we can remember it. So you want to evaluate, come back on, you need to evaluate the variance of k of x1 minus 3 plus, I can't remember it now, can you remember it? Let me just copy it across. Oh, I can't grab hold of it. Oh, that's because the pen's there. Okay, sorry about that. Let's just grab it and move it on. Just a moment, just paste it there. Okay, then let's get back to it. Sorry about the pause. There we go. So we want the variance of all of this. Could get a bit messy, but we'll give it a go. Alright, and I think just as we did before, I think it's probably best to factor out. We can distribute the variance over both of these guys here. So var of this guy plus this guy, we can split it up into k squared, the variance of x1 minus 3, plus 1/3 minus k all squared, the variance of x2 minus 3. But we know that the variance of x1 minus 3 is just the same as the variance of x1. And the variance of x1 is the same as bar of x. And the variance of x2 is the same as bar of x1. So all of this is actually k squared bar of x1 plus 1/3 minus k all squared times by bar of x2, which is the same as x1. So can you see that the value of k we choose is going to be some form of quadratic, and the value of k will obviously make the overall variability of the previous estimator change. So it's k squared plus 1/3 minus k all squared in a bracket times by var of x1. Now if we want to make all of this expression as efficient as possible, it maximises efficiency, we want to minimise the variability. And this is the original variability, which is fixed, so it's the k values here which we want to play with. So we want to take the k squared plus 1/3 minus k all squared, and we want to minimise this. Yeah. So this is where we should really just switch to the calculator, I think. Now let's just have a look. We've got k squared plus 1/3 minus k all squared. So let's just go to here. Let's do doc insert graph. We'll do x squared plus, in brackets, 1 minus, I don't think this is it, was it? 1 minus x all squared. I think it was 1/3, wasn't it, outside? We'll go back and check. 1/3. So quick peek. Uh-oh, where's my PowerPoint gone? PowerPoint is there. Okay, great. K squared plus 1/3 minus k all squared. Oh, terrible, long way off. Okay, that's it. Just graph that. We want the minimum value, which is somewhere here. So we'll do menu, analyze graph, minimum. And there's the minimum value of x is 0.167. That's there. So we just write that answer down, really. You know, k equals 0.167. Yeah, I suppose you could draw a little sketch if you wanted to. This is k here, and you've got this kind of thing going on here. Just shows that you've minimised a particular function. Yeah, I can differentiate it, but what's the point? You've got technology.